let us continue with the discussion from where we left. Any question regarding these three definitions? So, in our case, of course, the important criteria is the delay, the C2Q delay, because we are looking at the ripple counter. C2Q delay can be important, and if we look at the setup time, however, if we look at the counter operation, are we concerned about the setup time in our ripple counter? So, if I see where are we applying this, so you have the toggle flip flop being constructed, D, Q and Q bar, and we know that Q bar is connected to the D, and then you have the clock. So, each of the element in my design is having the Q bar connected to the D, and therefore, before the positive edge of in our case we have used the negative edge trigger. Just for the up counting operation we have used the negative edge trigger. So, before the negative edge comes, the Q bar is anyway stable, right. So, Q bar is always stable because much before the negative edge of the clock, Q bar was equal to the negative of Q. Therefore, Q bar was always stable. I do not need to worry about the sudden change in Q bar just before the downgoing edge of the flip flop in our case, because Q bar is connected to D. So, the D is automatically only the negative or inversion of the Q, which was stable all throughout the period, last period. Therefore, the setup time will not be an important concern in our case. However, clock to Q delay will be a concern because we are concerned with the total delay of the ripple propagation from the input to output. What about the hold time? Is it a concern? If you have bad transition times for the clock and clock bar, which are going into this flip flop, of course, I have shown one clock, but ultimately you have to produce both the clock and clock bar, which are going to control the TGs in this flip flop, and you are connecting the Q bar to the D. So, basically what you have done is this Q bar in this circuit is connected to the D, and if you have the clocks which are having say transition, my Q is supposed to change at the positive edge of the clock. So, whenever there is a positive edge of the clock, Q is definitely going to toggle, that is the operation of the toggle flip flop. So, at every positive edge Q is going to toggle, and therefore, at the positive edge of the clock we expect a transition in Q, it is going from high to low or low to high, and therefore, there can be, when you have a overlap between the rising edge of the clock and there is a significant overlap between the two phases, you can have a transparent path, and rather than Q bar getting reliably latched to the D, you can have intermediate undefined state, because you are connecting Q bar over here in D and all these latches are on for a given duration. So, it is not necessary that the Q bar will be reliably copied back to here, because the polarity from this Q bar to this point may not fall to 180 degree at that same instant, because all these latches are getting on together, and as a result I can have the wrong transition over here, and it can lead to erroneous phase in the counter output. So, the hold time will become important, and the rising falling edge, rise time fall time edge, and the overlap in the clock and clock bar will become important in our application. We would like to make sure that the rise fall time is not that bad, that when you are connecting this Q bar directly to the D, and for a short duration these are remaining on together, you are having a intermediate state, and the Q bar is not copied properly to the final Q. So, that is the only concern that we take care of. So, you should make sure that the rising falling edge of the clocks going to this transmission gate, they are not very bad, because otherwise it can lead to wrong latching. Because if you are trying to say Q bar over here, you have in this path you do not have any inverter. Therefore, logically if this remains connected over here to the D and both of them are having overlap, both of them are getting on at the same time, then basically what you are trying to do is Q bar and Q you are trying to connect together. The moment you have overlap and you are putting the Q bar over here, from here to here one inversion, here to here another inversion. So, you are trying to basically set Q bar equal to Q in that transition duration, which is not wanted. You can have an undesired output, you can have wrong transition over here. So, that is something to be careful about, and that can be ensured if you are having sufficient rising falling, sufficiently sharp edges of the clock and sufficiently small rise time and fall time. How does the rise time and fall time is controlled? So, just a brief discussion on that, so that we can end this discussion quickly. So, rise time and fall time of the clock are going to be controlled by the buffers or the inverters which are driving the clock. So, ultimately, as I said, the clock will be coming from some source which is having the signal 0 to VDD going in, and you may have a single inverter driving multiple transmission gates. So, a single inverter may be responsible for driving the clocks of multiple flip flops or multiple gates. You can have a single clock input going to multiple blocks. In our case, the first clock anyway comes to the first flip flop, and the output of the first flip flop goes to the next flip flop, and so on. But in case the output of a single source of the clock is driving many different blocks, then the load capacitance faced by this inverter or the driving circuitry can be pretty large, and as a result the rise time fall time can degrade. The moment you have more load connected to a particular driving gate, a digital gate, the rise time fall time can degrade. So, this is larger and larger number of blocks connected to the single driver or single inverter, you can have degrading rise time and fall time. Therefore, this condition should be avoided. In case a single gate is supposed to drive large number of other digital blocks, you can try to make the size of the NMOS and PMOS larger, so that correspondingly the current pumped in by this PMOS and NMOS also becomes larger, and as a result the rise time fall time is maintained. So, this is something to be careful about whenever you are using inverters or logic gates to drive the next stages, especially in case of clock. If the rise time fall time is too degraded, you would like to make the driving source or maybe the inverters with larger dimension, or you would like to use two inverters rather than using only one inverter. If this is the main clock, I can use two inverters. This is the CK, I can produce I can use two buffers and produce CK over here. This is a buffer, right? Two inverters together means a buffer, you have no inversion in this path. So, in that case, rather than the one single clock driving too many blocks, I can have effectively two clock sources. So, I have divided the single source into two sources, and therefore, their effective load capacitance will be halved. So, digital signal or digital clock can always be buffered. You can have bifurcation, and then you can have two sources driving the half the loads each, and as a result their fan out their total load capacitances will reduce. And there is an important definition of fan out that comes in digital circuitry, which deals with how many similar gates are drawn by a single preceding gate. So, in terms of analog circuitry, we talk about parasitic capacitances and load, etc. In terms of digital circuitry, because we are dealing with individual gates, we talk about fan out. So, in this case, if you have more number of gates being driven by a single gate, the fan out of that gate is large. So, here if you have three such gates, three logic gates, maybe AND gate or OR gate or NOT gate being driven by the previous gate, that means the fan out of this gate is 3. If you have n different gates driven by a single gate, the fan out of this gate is n times. So, larger is the fan out, you need to keep the dimension of these transistors also larger, so that it can supply appropriate charging and discharging current, and the transition can be faster. So, this is another important point. Whenever you are looking at digital circuitry, their transistor level implementation, you should take care of these fan outs, that a single gate driving many different gates, it will lead to degradation of rise time fall time. So, one option is you increase the size of the driving gate, other option is you split the signal, you use buffers like this, so that the load or the fan out of the individual buffers at the output is lower. Here, for example, I have split it into two halves, each of them catering to half the load. So, this can help you in retaining the overall shape of the overall sharpness of the rise and fall time of the data and the clock. Any question before we proceed? So, these are important considerations while looking at transistor level implementation. So, just like for the analog circuit and the switches, we have seen some considerations regarding the non-identical switches. When we are talking about the flip flops, it is important to be aware of the non-identities of the flip flop and be aware of the transistor level implementation of those flip flops. Another small topic related to the digital logic implementation is the logic we discussed for generating the phi 1. If you remember, we have the some small logic being used to implement phi 1. So, we looked at the counting operation, and whenever all the levels are turning high. So, you have say C1 to C7, all of them at some instance they are turning high and then finally going low, and we used the low phase of the clock, and we said that it is negative edge triggered, and we said that we are going to AND this clock bar and C1 bar, C2 bar, C7 bar to generate the phi 1 pulse. So, that was the phi 1 pulse was given by CK bar dot C1 bar dot C2 bar dot C7 bar. That is how we generated the phi 1 pulse. And the question was, if you want to have a wider phi 1 pulse, then only thing is you will have to use more such logic. So, for example, you want to have phi 1 pulses being a little wider. We consider the reason why we would like to have phi 1 pulse a little wider in the last discussion. The feedback of the op amp etc. can take more time. So, in case you are not able to speed up the feedback of the unity gain offset cancellation loop or the sampling circuitry, you may have to apply a longer phi 1. That is what we discussed, and for that only thing you need to do is apply more logic, that is the for more counts, like here I am talking about 1 1 1 1 all ones. Before that you will have 0 1 1 1 1, before that you may have 1 0 1 1 1 1 and so on. So, I will apply the logic corresponding to this combination and set them all to 0. So, whenever this particular phases are coming for the counter, I would like to keep for this entire duration, I would like to keep the phi 1 high. I can just use that additional logic. So, basically it will have another OR gate, another OR gate. So, if you get the first combination over here, I may not even use CK in that case. I will just use the count C1, C2, C7 bar. Then I will use say C1 bar or basically C1 or for example, if I have to keep the phi 1 on for a longer duration, and I am looking at this phase. So, just before this you have the phase all 1. So, I can keep this C1, C2 up to Cn, C7. So, this will be the phase just preceding this one. Before that you will have the phase C1 bar C2 up to C7 preceding just this one. So, suppose for these 3 phases I would like to keep the phi 1 high. So, I will just take the OR of this, this and this. Therefore, you calculate or you compute this particular logic using AND function, another AND function to calculate or to compute this particular combination, another AND function to compute the third one, and you OR them together, and therefore, the phi 1 will be remaining on for that entire duration. So, you have basically the AND gates taking care of this min terms, they are called min terms, combination of this AND functions, and then they are OR together. So, basically a bunch of AND gates followed by OR gates. Now, there is a question regarding implementation of these AND gates and OR gates at transistor level. How do we implement this? The basic structure we know for the for example, if you are trying to implement an NAND gate from which we can implement an AND gate, we know what is the NAND gate look like. So, it is something like you are having 2 input NAND gate where you have the input A and B coming here and A and B coming here, and we know that when both A and B are high, then the output will be low, and then you want to get an AND gate out of this. So, put an inverter. So, this is AND gate. Now, if you want to implement this function over here, can we go on adding? So, if I go for 3 input NAND gate or 3 input AND gate, I just need to add another C over here, the third transistor coming over here and another third transistor in the parallel. How does that parallel combination come? So, basically by the De Morgan's law, if you are having the A dot B, this output is supposed to go down when A and B is high. So, this is implementing basically A dot B bar. So, this NMOS combination is implementing A dot B bar, because when A and B both are high, the output will be driven low, and we know about De Morgan's law that this can be represented as A bar plus B bar. A dot B bar can be represented as A bar plus B bar. So, the PMOS circuitry over here should also support the same logic condition. So, when A dot B is high, then the PMOS should be driving it high. So, then we can see that when A here, if you have A low and B low, in both conditions output will be driven high, and that is basically nothing else but this function, right. So, this we can implement this A bar plus B bar by connecting A and B transistors in parallel using PMOS, because here when A goes low, then this pulls the output high, B goes low, then this pulls the output high. So, we take the we apply the De Morgan's law on the pull down logic and arrive at the transistor combination needed for the PMOS. So, here we are seeing A bar plus B bar, that is obtained by connecting these two in parallel, and they implement the same function. So, when this is trying to pull it down in the opposite phase, this will be trying to pull it up. So, both of them are satisfying the condition. Now, if we just go on adding these gates to implement larger logic functions, you will have stack of n number of transistors. You will have 7 transistors, 8 transistors coming in, and you will have a huge chain of transistors over here. So, if I want to implement the AND of these all these functions together, I will have to use such a stack, the C1, C2, C3, C4, C7 coming till this point, and also the corresponding C1, C2, C3, C4 coming here. And then ideally, of course, I can do this, and in digital circuit we know that we do not need to worry about the voltage headroom just like we do in analog circuitry. So, these are just triode region switches, and ultimately the voltage drop across them can reach to 0. So, I do not worry so much about the triode the voltage headroom across the switches in digital operation, but what I do need to worry about is the transition delay. So, if you are stacking too many transistors in this fashion, each of them are going to add to the overall transition delay of the discharge path, and that increases as n square. If you have n such transistor, the overall transition delay of this logic increases as n square, because effectively you are having parasitic capacitances at each point, which is increasing with n total capacitance charged, the worst case, and also you have the total R in the series connection, which is also increasing with n. Therefore, the total delay can be shown to be proportional to n square. So, if you stack more and more transistor to implement such logic, it can increase the delay steeply. Therefore, generally people do not go beyond 4 input. So, maximum number of input that you can see in libraries standard cell 4 input, better is maybe 3 inputs and so on. So, beyond 4 input it can degrade the delay pretty significantly. So, in our case, since we are having say 7 or 8 input, in our original case we started with this particular combination CK bar, C1, C2, C3, C7. So, we can split it into 2 halves 4, 4, and then implement the CK bar, C1 bar, C2 bar up to C3 bar, and then another one, and then AND them together. That can be one solution. So, I can, rather than implementing the entire function using a single gate, I will split them into 2 halves and then combine the result. So, basically I am going to look at CK bar, C1 bar, C2 bar, C3 bar, and another one C4 bar, C5 bar, C6 bar, C7 bar, implement them individually using gates and then take their AND. And if I look at this, this is if I look at A bar, B bar, you know that this is nothing is but A plus B bar. So, I can also represent, I can extend it to the larger number of inputs also. Therefore, this can also be implemented as NOR gate. So, I can just have CK plus C1 plus C2 plus C3 NOR given as this combination, and then it is ANDed with C4 plus C5 plus C6 plus C7, and then again you have the NOR of these two. So, basically you need to implement 4 input NOR gate and then AND the result together, and as a result means NOR gate can be implemented using once again similar scheme, only thing is the combination is just opposite. So, you have the NMOS in parallel, the 4 NMOS coming in parallel, C1, C2, C3, CK, and then you have the PMOS coming in series, because if I take the this is going to be low when the any one of these is high, and then the negation of this, the De Morgan's, we know the negation of this is going to be this CK bar, C1 bar, C2 bar, C3 bar. So, that comes in series. So, C1, C2, C3, C4. So, this is a 4 input NOR gate. I can take 2 such gates and apply arrive at these 2 and then combine them using AND gate. So, that can be possible implementation. And one important point to be noted is, in general, you can have the PMOS mobility. The mobility of the PMOS in 1 nanometer can be half the mobility of NMOS, and as a result, the speed of the PMOS transistor can be half the speed of the NMOS transistor for the same dimension. So, therefore, if you stack PMOS transistors, it leads to slower speed rather than if you stack NMOS transistor. If you are stacking NMOS transistor, the speed for 4 stacked NMOS transistor can be better, significantly better than the speed of 4 stacked PMOS transistor, because the mobility of the PMOS is slightly lower, or rather 2 times lower in 180 nanometer. That difference has vanished for lower technologies. For lower technology node, that difference is very minimal, but for older technologies 180 nanometer is still at least 2 to 2.5 ratio you will get. So, generally for high speed logic we may prefer NAND gate implementation, but in our case that is not an important concern, because we are not that where logic speed is not very high. As a result, we can go for NOR gate implementation also. So, you just should be aware of the logic design. If you are supposed to implement any logic gate using transistors, you should know how to split it and how to implement it using smaller gates, so that the delay is within limit and you are having right kind of transitions. If you are along with the delay, of course, another point is rise and fall time. If you stack more transistors, because of the large RC time constant, the rise time fall time will also be degraded. So, these issues should be kept in mind while implementing transistor level logic. Any question before we end this discussion? So, we have basically covered the building blocks of our ADC in sufficient detail, starting from the ramping circuitry, comparators, their non-agilities, sampling circuitry, along with the comparator design, its specifications, its non-agilities, including offset cancellation, and finally, we also came into the digital controller part, where although the control is simple, but we dealt with the constituent blocks, constituent elements at block level, overall functionality of the control operation, how the 5152 pulses are getting generated, and finally, we went into the transistor level implementation of all those digital blocks, looked into the important definitions and issues at transistor level implementation of those digital components. So, this basically completes the overall controller module that we have for the A to D converter. Any question before we end this discussion?
Sir, if speed of PMOS is slower, then will the output synchronize?
Synchronize means clock, with respect to clock edge, you will have little bit more delay if you are applying the input to a PMOS or applying the input to a gate where you have more PMOS stacked, the delay will be slightly longer. So, as compared to the clock edge, the delay may be slightly more. That is the only thing. When the NMOS is off, then if the lower branch is off, then only the upper branch will be turning on and will be charging the capacitor. So, they are not on at the same time. So, there is no fight, they are complementary. One is off, then only the other goes on.
So, in case of bifurcation, you added 2 inverters buffer. So, why can't we simply divide it into 2 parts without adding the buffer?
So, if you do not add the buffer, then how are you going to if you do not have this inverter, then the load capacitance remains same. That is the main purpose, right? So, dividing the load capacitance and making it smaller. So, if this was connected to 8 logic gates, then the fan out of this was 8. Now, I inserted some buffers, and then this buffer is driving 4, this buffer is driving 4. So, fan out of each of these is 4. Any other question? Okay. So, we can end the discussion and resume with a new topic.